So, we start the course on distributed computing systems. So, the name of the course that is there in the IIT curriculum is called distributed systems. Now, distributed systems includes a lot of different types of systems which are distributed in nature, but what as a computer scientist what we must study is the computational challenges that lie behind implementing a distributed systems. So, though the course is about distributed systems, we will start the course by looking at the major problems that come when we try to implement a distributed system, and thereafter we will see some applications of distributed systems in the later part of the course. Okay. So, the books that we are going to follow mainly are the following. There is a book on advanced concepts in operating systems by Singhal and Shivaratri. There is a McGraw-Hill International edition for this book. Then there is an introduction to distributed algorithms by Gerard Tell, which for again for this book also there is a low cost edition available for India and South Asian countries. So, these are the two books that we are mainly going to follow. Okay. Copies of all the slides that I am going to use are there in my web page. So, you can always download them and keep them available with you whenever you want. So, let us start with a definition of what is a distributed system. So, can any one of you give me an example of what you mean by a distributed system or an example of a distributed system? Network is actually the vehicle over which we implement a distributed system. So, we know it is distributed. So, it will be implemented over multiple machines which will communicate through a network, right. So, network is the backbone of the thing, it is the architecture. But what is a distributed system? E-banking, yes, that is a nice example of a distributed system, where the database, the bank database is stored somewhere and you are accessing it from a remote place. But even then that is not purely distributed. E-banking will be distributed if the actual data, the bank data is stored in many different places, right. So, when we talk about a distributed database where the data is probably replicated or fragmented and kept in different machines, possibly at different locations in the country or in the world, then that is a distributed system. Now, then we have to take care of things like when I update an account here, have I updated all copies of the account wherever they are replicated. Okay. So, we have to be, and so that is one example of a distributed system. Okay. To implement a distributed system, we need the network, we need a distributed architecture, we need distributed operating system level control, then we need distributed application development mechanisms. How do we develop a distributed application? And then we have the actual application which has to be conceived as how we partition the data, how we partition the methods that will apply on those data, and that brings up the complete distributed system. Okay. So, a very broad definition of a distributed system is a set of autonomous processes communicating among themselves to perform some task. The issues in implementing such a system is primarily unreliability of communication, because at the lowest level communication may be unreliable, lack of global knowledge, a process running on one machine may not know the status of a process running on another machine, lack of synchronization and causal ordering. When we talk about distributed systems, we do not assume that they are synchronized, in the sense they are not driven by the same clock, they do not have the same definition of time. So, whenever you have different processes running under different clocks with different notions of time, then causality is a very important thing. I mean, when we try to say that this should happen after that, how do we implement that after, because they are running on different clocks, they have different notions of time. So that is one another problem. So lack of synchronization and causal ordering. Then concurrency control. Concurrency control, as we shall see, is one of the very fundamental challenges when implementing a distributed system. And then finally failure and recovery. Failure is that parts of the distributed system can go down, but that should not ideally lead to the collapsing of the entire system. So how do we recover from that? How do we make the system fault tolerant? So these are major issues. The advantages of distributed systems are that we have resource sharing, because if you have heard of cluster computing, right, where you have a cluster of machines, and then if you individually allocate those machines to individual students, then they are going to, each student is going to use a particular machine for X% amount of time, right. The remaining time the machine is idle, right. So it makes sense that if we, instead of doing that, if we do a load balancing, when I have many processes to run, I could siphon off some of those processes to another machine, and then it runs there, because that machine has less load at that point of time. Okay. So that kind of strategies typically help in better utilization of the resources. Another very important thing which is driving cluster computing is power. If you look at the kind of power consumption that data centers have, then that is huge. You know that there people are actually building data centers under river beds, so that they can, it cools faster. So that gives you an idea of the magnitude of the problem. So much of heat is generated from that set of systems in a data center that it is very difficult to, you spend more on air conditioning than you spend on the actual servers, because you will have to keep the place cool, and the amount of air conditioning that you will spend for that is going to cost you more than the cost of the servers. So that is why it is very important to see that the resources are properly utilized, in the sense that computation, when it is sparse, then they can be clustered into some set of machines, and the other machines can be in a power down mode. So that saves a lot of power, instead of keeping all the machines up all the time. The other advantage is high performance, because we can use parallelization. We can have things running in parallel on multiple machines, so we can complete tasks faster. You can have fault tolerance. Why? Because you are treating it as a distributed system. If any part of it goes down, the remaining part machines will cooperate together to solve your problem. And scalability. Scalability is also an advantage, because we are learning how to build scalable distributed systems, so that we can handle larger and larger amount of information and data, which we could not do if we just look at standalone machines. Let us see some examples of the kind of challenges that we will look at in this course. So to start with, I will talk about a nice problem here. So this is a story about a fort. So this is a fort, and there are two armies which are camped on two sides of the fort. Okay, and this army has general 1, this army has general 2. Okay, now general 1 sends a message to general 2 indicating that we want to attack the fort tonight. Okay. Now the problem is that once the messenger travels around the fort, there are archers on the fort who can shoot the messenger, and if the messenger is shot, then the message will not reach G2. The problem is G1 does not know whether the messenger has reached or not. Okay. Now, if any one of them attack, then they will be crushed. The success of attacking the fort depends on both of them attacking together from the two sides, right. Now, look at G1's problem. G1 has sent the message, but it does not know whether it has been received or not. So, will G1 attack? It will not. So, what does G1 need in order to? It needs an acknowledgement from G2 that yes, I got your message. Now, look at the problem. When the messenger reaches G2 and G2 sends an acknowledgement, now G2 does not know whether this acknowledgement will reach G1, right. So, it could be possible that this acknowledgement messenger is killed, then G2 does not know whether G1 has received the acknowledgement, but G2 knows that if the acknowledgement does not go, then G1 will not attack, right. Now, look at G2's problem. Will G2 attack? No. So, G2 needs what? It needs an acknowledgement from G1 that the acknowledgement had reached, right. So, again G1 must send an acknowledgement. Now, if this acknowledgement does not reach, G2 will assume that G1 did not get the acknowledgement and so will not attack, right. So, G1 cannot attack until it gets an acknowledgement to this one now. So, where are we going to terminate? So, you see this is a very fundamental problem. We are trying to communicate one bit of information from node A to node B, and we are assuming that the communication medium is not reliable. Then for every message that we send, we want an acknowledgement and an acknowledgement for an acknowledgement and an acknowledgement for an acknowledgement, and this goes on. So, how are we going to solve this problem, right? So, there has to be some assumptions about the network that a packet sent infinitely often is eventually going to reach the destination, right, and there has to be some way of progress. So, you see the fundamental single bit communication itself has some fundamental theoretical challenges, right. So, we will see how we have overcome this, how we have built robust networks, how do they guarantee that whatever data is being transferred is actually correct, and so on. The second example that I am going to give you, these are all to motivate you to the nice problems that we have in distributed systems. Second is the problem of not communication, but of knowledge sharing. Now, you know, knowledge is something that is not just sharing of information. It is about knowing that something is true and about something is false. So, the muddy forehead problem is a very well known problem, which some of you have heard of it, no? Okay. So, two children, they come home from the playground and their mother tells the children, addresses the children and says that whoever has mud on your forehead, please go and wash. Okay. Now, the child itself cannot see his own forehead, right. So, both children wait for one moment and then they go, both of them go for washing. Now, what is the logic behind this? So, in the first instance, this child 1 can see the mud on child 2's forehead and child 2 can see the mud on child 1's forehead. Now, suppose one of them did not have mud on their forehead, then the other one would have seen that okay, my brother does not have mud on his forehead, so it must be me, right. If the other person's forehead is empty, then it must be me that has mud on my forehead. So it would have gone and washed in the first time instant, right? But he did not. Why? Because he found mud on his brother's forehead also. So in the second time step, both brothers will reason that why did he not go to wash in the first time instant? If I did not have any mud on my forehead, then in the first time instant he would have gone and washed, but he did not. Why? Just because I did not, right? Because we both have mud on our forehead. So he was waiting for me to go and I was waiting for him to go. So in the second time instant, both have the knowledge that they have mud on their own foreheads, right? So this is you see that this is how the communication of information builds on the knowledge, and there is a reasoning component in it, right? And that reasoning is by which you understand things and accumulate that knowledge. Okay. In our Indian philosophy, there is a difference between knowledge and realization, which is a very important distinction. Knowledge is when you collect this information and understand something, and realization is when you actually understand the concept behind it. For example, think of colors. How does a baby understand colors? So we tell him that this is a red pen, okay, this is red, and we tell that okay, this is black. So maybe it thinks that okay, things which have a shape like this are called red and the square ones are called black, right? So that way it starts learning that okay, this is red, this is black, but it still does not understand color. It still does not understand why this is red, okay, and why this is black, okay. So after a lot of training, you present it with a red ball and say that hey, this is blue, because it had seen a blue ball and it has understood that all ball like things are blue. And then the mother gets really annoyed and says that my child will never learn colors. And then the day on which the child realizes what is the meaning of color, suddenly she is able to identify all colors, right. So that is the difference between this. So in distributed systems, we will see a lot of cases where a lot of information flow will take place, but the realization of a particular concept will again come through some reasoning and understanding at the end. Okay. So let us proceed further. Now this is one of the most difficult distributed examples of distributed control. Now as you may be aware, you know, I had a idea that the largest consumer of Pentiums is the desktop or the home computer or the office computer industry. It is not. The largest consumer of processors are the cars, automobiles. Why? A modern automobile is going to have anywhere between 25 to 30 processors. Why does that happen? Because everything in a modern vehicle is computed by is controlled by a processor. So the amount of fuel that is going to be injected in your engine, given the speed at which the vehicle is traversing, given the amount of friction that the wheels are experiencing, the amount of fuel that has to be injected is decided by a processor. When you are driving a vehicle which has a power steering, what is a power steering? You turn the steering, there is a sensor which checks how much of turning you are providing, and there is an actual motor controlled by a processor which is turning the wheels. Otherwise, you will find it extremely hard to drive a large vehicle like a Hummer or a Sumo. Okay, you will find it very hard, or a huge truck. You will see from a huge truck, these days you will see a very thin driver coming out. No, he manages to drive that truck because of the auto steering, because of the power steering facility. So, and even when you turn the steering, there is a feedback given to your steering. So, when you are traveling at a high speed, you will find that it is harder to turn the auto steering than when you are traveling at a lower speed. Why? Because it gives back the same feeling as you would have in a normal driving environment. All this is controlled by processors. Okay. Then the body temperature, how much of temperature has to be maintained inside the vehicle, that is controlled by a processor. The centralized door locking system is controlled by a processor. The power windows are controlled by processors, and they are very sophisticated things. You can put your head on the window, outside the window, and then your child presses the power windows, you can get throttled, right? The window will come up and throttle you. So, there are sensors there which will immediately stop the power window in this if it feels that there is a obstacle. So, these are very sophisticated features, and these are not all manufactured by the car company, they are manufactured by different vendors, and then they are shipped back to the car company and assembled by the car company. Now, what happens is, with each of those embedded systems comes its own control processor. So, if you have 30 subsystems in the vehicle, you have 30 processors, right. Now, you have the vehicle level safety features to build in. What kind of safety features? There is a camera sitting in front of your vehicle which detects pedestrians. Then there is an automatic braking that must take place. If there is a crash situation detected, the steering will collapse, the airbags will come out. Now, this is not something which is implemented on one of those systems, it is something which is implemented over multiple systems like that. Now, this is where distributed applications are coming up, and now it is very difficult to implement this over all these different subsystems which have been procured from n different vendors, right. And the automotive industry is moving towards a new direction now. What they are doing is that they are saying that, look, when we buy a printer, do you buy another computer to run the printer? You do not. The printer comes with a driver software. The driver runs on your machine, right, on your processor, and controls the printer. Why can't we do it for automotive? The subsystems will come, but we will not have 30 processors, because that is too difficult to integrate and manage the distributed system. Let us have 5 to 6 processors on the vehicle, and all those control software will come as plug and play. You connect the embedded system, load the software, and it should run, right. That is the main challenge that the automotive industry is gearing up to today, right. And there is a phenomenal amount of research opportunity there, because as you can see, it is going to just turn around the way in which automotives were designed. There is a center, there is a collaborative research lab at IIT Kharagpur with General Motors, which came up in December 2007, which addresses some of the issues on automotive embedded control, and it is a fascinating distributed control problem. Okay. Why is it hard to design distributed systems? The usual problem of concurrent systems is arbitrary interleaving of actions makes the system hard to verify, because there are, for different sensor inputs that the distributed system gets, it produces different outputs. Okay. So, you will see a distributed algorithm is written in a completely different way as compared to the algorithms that you have studied. A distributed algorithm will typically look like this, that there will be some precondition okay. Whenever this is satisfied, there will be some action which is executed, right, and this action will typically leave some side effects, or which you might call post condition, and this is going to be a process which is going to be replicated in many different sites. So, you will say that this is the code for process P in the ith location. Okay. Pj will be similar, except that it is executing on a different machine. Now, see, the way that this works is, this precondition is typically some input that is coming from outside. So, it is a combination of its own state and some input which it receives by virtue of messages or some inputs in the local site. Okay. Then the action is executed, and then the corresponding side effects or the post conditions must hold. If they do not hold, then probably there is something wrong in the particular process. Okay. This is how you will see that most of the distributed algorithms will be described. Now, because the messages can arrive in arbitrary order, these actions can be triggered in arbitrary order, right. So, you can have action A1 followed by A2 or A2 followed by A1 depending on how the message is reached, right. So, you have to make sure that the algorithm will work for both of these cases. So, the verification problem is harder because you have to verify that the system works for arbitrary interleaving of the ways in which the messages arrive. The next problem is there is no globally shared memory, therefore, it is hard to collect the global state. How do we find out what is the global state of the system? That is a very hard problem. Yes. Side effects is a post condition. See, what is this action supposed to achieve? That is the post condition. We say that if this precondition holds, this action is executed, then the result of that action will be such and such thing. So, the post condition, like the precondition, is not an executable. The precondition is what you need to trigger the action, and the post condition is what you need to check at the end of the action, that should have happened. If it does not, then we are in an error. Okay. The other problem is that there is no globally shared memory. So, therefore, it is hard to collect global state. Okay. We will see how to implement global state collection algorithms. There is no global clock, and there are unpredictable communication delays. Okay. Now, we will study distributed algorithms under different topologies. So, topology is the way in which the backbone network is connected. Okay. So, completely connected, it could be a ring, a tree, or any arbitrary graph. Now, when we talk about this topology of this thing, this is the view that the algorithm has of the underlying topology. So, even though the underlying topology is a LAN, where we assume that any node can send a message to any other node, the distributed algorithm might want to look at it as a tree, in which case it will only send messages along the branches of the tree. Okay. So, when we talk about topology, please do not think that that is the topology of the network. It is not the topology of the network. The network can be anything. The distributed algorithm views the set of nodes as a tree or a ring or whatever way, and the communication between the nodes, the message passing between the nodes is done based on that topology. The communication can be by shared memory, it can be by message passing. So, the reliability is an issue, the delay of messages is an issue, the FIFO, whether the messages are delivered in order or whether they are delivered out of order is one issue, and whether the messages are broadcast or sent point to point or multicast among a subset of the nodes. These are the things that we have that will distinguish one distributed system from another. Then distributed systems can be synchronous or asynchronous. Similarly, the algorithms can be synchronous or asynchronous. And the failure models can be fail stop, then crash. Crash means that the machine completely goes down. Omission, okay, in the sense that sometimes it is down, sometimes it is up. Byzantine, in which it becomes malicious, it tries to do things to thwart your algorithm. Okay. So, when we have an algorithm, our algorithm needs to specify the model on which it is supposed to work. Okay. So, we will first define the topology, the communication model, whether it is synchronous or asynchronous, what is the failure model, and then we will say that this algorithm works on this model. Okay. Complexity. How do we define the complexity of a distributed algorithm? So, there are several different metrics for evaluating the complexity. One is the message complexity. How many messages does the algorithm exchange? So, that gives you an idea, because in many cases the network bandwidth is the main bottleneck, right. So, the number of messages that you need to send or the message complexity can actually be an important factor in the runtime of the algorithm. Communication complexity. This talks about not the number of messages, but actual number of bits, because the messages can be of variable size. So, you may actually want to measure the complexity in the number of bits that are communicated. Then we have time complexity. For synchronous systems, the time complexity is measured in the number of rounds of the algorithm, the number of rounds of message exchanges. And for asynchronous systems, there are many different definitions which we will see from time to time. We are going to see several problems in this course. So, this is how the course is going to progress. So, now think of a distributed system. If we start from the bottom, okay, at the bottom most point, what do we have? You remember, have you done a networks course? How many of you have done a networks course? Okay, quite a few of you. So, in a computer network, you know the ISO OSI stack, right. So, at the lower layers we have the data link layer, okay. Just above the physical layer we have the data link layer. So, in this layer the main issue is communication of bits, right, from one side to the other. So, we will see first that how do we establish robust communication at this level. Okay. We will see what are the algorithms that help you achieve robust communication at this level. Then we look one level above that, where we look at packets. Okay. So, this is the IP layer, right, where we have packets, and these packets will have to be routed through possibly other nodes to the destination, right. So, we will look at routing problems here. What are the routing algorithms at this level? Okay. Now, other than routing, there is another important problem that is there here, is that when the packets are routed, they are stored and forwarded. So, they are stored from one node, then forwarded and then stored in the next node and forwarded. So, there is a buffer management problem here. Okay. So, we will see how we do buffer management in these layers. Okay. Then we will rise one more layer where we will talk about messages. Okay. Now, we are not talking about individual packets anymore, we are talking about messages which can be a collection of many packets. We will assume at this level that the lower layers are robust and working correctly. So, if I send a message as a whole, it will get received as a whole. Here we are going to look at things like how do we implement a global clock, and how do we order messages. So, how do we implement ordering of messages, assuming that though the messages are delivered correctly, they may not be delivered in order. So, M1 is sent before M2, but M2 is received before M1. How are we going to resolve this, and at the destination side how are we going to order the messages in the sequence in which they have arrived. Okay. So, that is what we will study at this level. Then above this we are going to look at algorithms which uses this message communication and communicate knowledge from one node to other nodes. Okay. So, we are going to look at classes of algorithms like wave and traversal algorithms, which are going to talk about how information is propagated in a distributed network and how we can achieve meaningful computation out of that. So, we will see that many different types of algorithms like leader election, like termination detection and constructing spanning trees, etc., can be implemented as variants of wave and traversal algorithms. Okay. And then we are also going to look at knowledge sharing and knowledge agreement of knowledge. So, we are going to look at agreement protocols. These are very nice and interesting agreement protocols. The muddy forehead example was one example of agreement protocols. We are going to see some of them. Now, this is going to be which is going to come under the distributed computing area, because all of these are fundamental to any distributed system which is implemented. All of these problems appear in all distributed systems. Then above this we are going to look at distributed databases, we are going to look at the issues that arise in distributed databases, we will look at concurrency control and things like that, which are more specific to specific domains of distributed systems. Okay. So, that is about what we are going to cover in this course. So, thank you for your attention.